restriction. First of all, I'd like to welcome all of the audience here. It's a good afternoon for all of you. It's a great pleasure to have today Dr. Judy I. So thanks for accepting the invitation to, not to be here personally, but to be here in a virtual way. So thanks very much. It's a great pleasure for us from the University of Campinas, from the Chemistry Institute, to have you here. So I'll just say some words about Judy. So Judy grew up in the subtropical island of Taiwan. She earned a BS in chemistry. I think I can say the year, it's not too bad, 2004. From it's Tonghai University. How can I say?
Tonghai, yes, Tonghai. Very good
pronunciation. Okay, Tonghai University in Taiwan. And a PhD in 2011, worked with Paul Schleier. It's correct, Schleier?
Yes, yes.
At the University of Georgia, US. In 2015, she began independent career at the University of Houston, where she's working from 2015. You just mentioned some words that Dr. Judy I. It's a UPAC Young Chemist Award. It's a National Science Foundation Career Award. NIH, it's MIRA Award. And this year, she was selected as a Sloan Research Fellow. So she published more than 7 papers, in fact, 8 papers. This year, its 11 paper was accepted and published this year, so it's very impressive. So this is related to the people that are working hard from home, so probably. And
yes,
so,
I think a lot to do with that.
Yeah. So once again, I'd like to thank you, and please, you can start when you are ready. Thanks very much, Jude.
Okay, well, thank you, Claudio, for arranging the seminar and for inviting me. I hope next time we meet in person. Let me start my presentation. So you can see my screen now?
Yeah.
Okay.
Yeah.
Let me play from the start, and let me do I think I can choose laser printer.
Yeah.
Laser printer. I will use a blue one. Okay, so my discussion today is centered around basically 3 keywords, and you can see these keywords in my title, and those are excited state, proton transfer, and anti-aromaticity. So the story is going to be a relationship between these three phrases. Now, what I want you to do first is to think about a hydrogen bond. You have a hydrogen bond donor and you have a hydrogen bond acceptor, and in between a proton is shared. Now, when light strikes this hydrogen bond, one of 2 things can happen. One thing that could happen is that the proton will move towards the hydrogen bond donor. The other thing that can happen is that the proton can move towards the hydrogen acceptor. And now in the extreme, you can imagine that it might go to the other side. So when light strikes a molecule that has a hydrogen bond, one of these 2 things can happen. And today my story is to tell you that whether this happens or that happens depends a lot on the anti-aromatic and aromatic character of molecules. You can see me also, right?
Yeah.
Okay, good. Okay, so let me start with a 1-minute story. Consider a molecule like this. So this is O-salicylic acid. You have 6 pi-electrons in a ring. You have a hydrogen bond donor. You have a hydrogen bond acceptor. So these are some of the obvious features that you can see in orthosalicylic acid. It's 4n plus 2 pi-electrons, so you can consider it aromatic. Now, when light strikes an aromatic molecule like the salicylic acid, something happens. And what happens is that 4n plus 2 no longer means aromatic. 4n plus 2 becomes an anti-aromatic electron count. And so the orthosalicylic acid becomes excited state anti-aromatic. And that makes the molecule very reactive, just like any of the other anti-aromatic molecules that you can think of. Cyclobutadiene, pentalene, cyclopentadiene. And so what happens here is that a proton can quickly shift from one position to the other position. So a hydrogen bond relationship becomes a proton shift relationship. And you get to this tautomer. Now, if you look at the features of this tautomer, you will notice that the cyclic delocalization is now breached. So now you have a quinoid form. And so in effect, what you see is that when an aromatic molecule is photoexcited, it becomes excited state anti-aromatic, but proton transfer is one way to quickly relieve that anti-aromaticity. And this is one example of that. So proton transfer disrupts cyclic pi delocalization, and it relieves excited state anti-aromaticity. Okay, that's my 1-minute story. The implication is that that is one example, but we actually find that in many cases of excited state proton transfer reactions, you see the same patterns. So here I put together some examples of excited state proton transfer systems. The first one is the salicylic acid example that I just showed you. There are biprotonic transfer examples. So proton transfer, 2 protons transfers at the same time, 1 to here, 1 to here. There are dynamic catalysis of proton transfer. There are proton relay transfers involving hydrogen bonding solvents. Now, a main theme that you'll probably see in all of these examples is that the molecule, the starting molecule, is ground state aromatic. So you count the electrons, 1, 2, 3, 4, 5, 6. So that's 6 pi electron ground state aromatic. 6 pi electrons ground state aromatic. 14 pi electrons ground state aromatic. 10 pi electrons ground state aromatic. Now, when light strikes, when light shines on these ground state aromatic molecules, they all become excited state anti-aromatic. And a very easy way to relieve that anti-aromaticity is to transfer a proton, either within the molecule, with a solvent molecule, with another substrate molecule, or through a series of solvents. Okay. Okay, so before I continue with my story, I want to give you a little bit context on anti-aromatic molecules. We learn a lot about aromatic molecules, but the concept of anti-aromaticity is a little bit less familiar. But basically, as you can see here in this very reactive slide, when molecules are anti-aromatic, they are highly reactive. So think about molecules like cyclobutadiene that quickly dimerize even at a very low temperature. Pentalene is very difficult to make unless you tether it with fused benzene systems, or cyclopentadiene, which is very difficult to make unless you put very bulky groups, for example, tert-butyl groups all around, then that's one way of trapping it. But the bottom line is that when a molecule is anti-aromatic, it is not very happy with the state, and it wants to quickly get out of the state of being anti-aromatic, and that usually leads to some reactions, and in these cases, dimerization reactions. Here's another example. So here's another example of an anti-aromatic molecule. Benzene is ground state aromatic, but when it's excited to a first excited state, it becomes anti-aromatic. So here you see the ground state benzene having 2 pi electrons here, 2 pi electrons here, 2 pi electrons. So that's the ground state 4n plus 2 pi aromatic configuration of electrons. Now, when you excite an electron, so here I'm drawing the first excited state, you move 1 electron from here to here, it becomes excited state anti-aromatic. And this is actually a concept that was proposed quite some time ago by Colin Baird. We met him last year in Sweden. Here's a picture of me, Colin Baird, Lucas, and a funny Italian guy, Stefano. And so what Colin Baird proposed in 1972 was that the rules for ground state aromaticity are reversed in the first pi to pi star state. So this means that if you have a 4n pi ring, it's aromatic. And when you have a 4n plus 2 ring, it becomes anti-aromatic. So in this case, you see that benzene has 6 pi electrons. So 4n plus 2 makes it ground state aromatic, but excited state anti-aromatic. And so what does benzene do when it's excited state anti-aromatic? Well, just like cyclobutadiene and pentalene and cyclopentadiene, it becomes highly reactive. And in the case of benzene, it quickly isomerizes to fulvene, or examples like benzvalene, which is highly strained and explosive. This is basically a powder that you can scratch it and it will explode. And so the message is that molecules really do not want to be anti-aromatic. When benzene is excited state anti-aromatic, it rather explodes than be anti-aromatic. And so it rather transforms to a highly strained structure. And so the message that I'm trying to get across is that molecules do not want to be anti-aromatic, and the way to do that is to undergo some kind of reaction. And this example of benzene is quite an extreme one, but you can think of other milder ways of getting rid of anti-aromaticity. Okay, so now let's do a little bit of a thought experiment. You start with benzene and you put some hydrogen bonding functional groups on it. Here's the example of it. We just saw the salicylic acid example. You take benzene, you put some hydrogen bonding functional groups, a hydrogen bond donor, a hydrogen bond acceptor. Now this molecule still is ground state aromatic, and when you photoexcite it, it becomes excited state anti-aromatic. But now there's a milder way of getting rid of anti-aromaticity, and that way is to transfer a proton from this site to the other side, and it breaches the cyclic delocalization in the ring, and then you get rid of excited state anti-aromaticity. Now this effect actually has been known for a long time. This is a picture copied and pasted from the original paper of Weller in 1956, where he did an experiment looking at the UV spectra of O-salicylic acid. So what he noted very interestingly is that if you take a UV spectra of O-salicylic acid, you will see two emission peaks. So this shift in the emission peak suggested that there's the appearance of a rare tautomer. Now this effect, where a new peak appears, this effect has many names in chemistry. So spectroscopists call it a Stokes shift, and organic chemists, they call it a photoacidity of the compound, and some theorists call it a change in the feature of the wave function, which is basically everything. But what we want to say is that this change is actually triggered by relief of excited state anti-aromaticity when a molecule when an aromatic molecule is irradiated. And so you see this is a nice cartoon drawn by one of my students, Lucas Caras. So here you see the salicylic acid right here. It's photoexcited. Now it's green and anti-aromatic. He's talking to this tautomer and asking him, how did you get rid of this anti-aromaticity? And he says, oh, I transferred a proton. So proton transfer is one way of relieving excited state anti-aromaticity. Now this paper was published last year in PNAS 2019. The original title of the paper is this: Excited state proton transfer, molecules in a hurry to get rid of anti-aromaticity, paired with this very nice cartoon that I like very much. But this was considered to be a little bit too boutique-like for PNAS. So they said, no, we don't want your title. Please find something more serious. And they also did not accept our picture. And so finally, we have this somewhat boring title, but still descriptive: Excited state proton transfer relieves anti-aromaticity in molecules. If you're interested, you can find this from my website, or you can find this online to read more about it. Okay, now I'm going to tell you the exact same story, but now this time with numbers. So when you have an aromatic molecule and light strikes the aromatic molecule, it becomes anti-aromatic. And one way to relieve that anti-aromaticity is to shift a proton within the molecule, just like the salicylic acid example I just told you about. Now, this is that example that we just talked about. You have orthosalicylic acid, and when you photoexcite it, let's say to the first excited state, it becomes excited state anti-aromatic, and shifting a proton from the hydroxyl group to the other side relieves that anti-aromaticity. Now, interestingly, if you photoexcite salicylic acid to the second excited state, now no proton transfer is going to happen. Now, one way in my group, one method that we use to quantify aromaticity is to use this method called nucleus independent chemical shifts. So you don't need to understand the details of it. This is basically a computational NMR. So instead of using a atom as a probe, you use a dummy atom, or not a ghost atom, sorry, a ghost atom. It actually has a name, Banquo, following the story of Macbeth. So that you put this Banquo atom anywhere within the vicinity of the molecule, and you use it to probe the shielding effect of a ring current. Now, generally, we put the probe inside a ring, and if you get a negative value, it means you have an aromatic ring. If you have a positive value, it means you have an anti-aromatic ring. So here you see the effect. Salicylic acid in the ground state is aromatic. You photoexcite it to the first excited state, it's anti-aromatic. And proton transfer, you see here that as soon as the proton transfers, the salicylic acid in the excited state relieves a lot of the anti-aromaticity. And so you see the effect of anti-aromaticity relief right here. Now look at the second excited state. If you photoexcited to the second excited state, the molecule still is aromatic, and so there is no need to transfer a proton to relieve any anti-aromaticity, and therefore no excited state proton transfer reaction happens. This switching of aromatic and anti-aromatic character was actually found also by Peter Karadikov in 2016, where they find that helical aromatic rings with 4n plus 2 pi-electrons, they become anti-aromatic in the first singlet excited state, and then they switch back to aromatic in the second excited state. So you see that here. Okay, now another example. So these compounds, you probably see these around a lot, where you have 2 pi-conjugated systems tethered by a single bond, and there are some hydrogen bonding features here, where when you shine a light, the hydrogen bonds, the proton transfers to the other side. So these molecules people are interested in them because of their applications as fluorescent probes and dyes. Now, the effect that I want to emphasize here is that this excited state proton transfer also is an example of anti-aromaticity relief. So here I have two forms of the tautomers of the same of a molecule. The A form, where you see 4n plus 2 pi ring over here, and a Q form. I call it a Q because you have a quinoid structure here. Now in the ground state, the more aromatic form, so the A form, is lower in energy by about 12 kilocalories per mole. When you photoexcited to the first excited state, the 6 pi electrons in a ring becomes anti-aromatic, and now the Q form is actually lower in energy by 4 kcals per mole or so. And you can consider it in either the S1 state or the T1 state. The trends are the same. Now, if you consider the computed Nix, so again, the negative Nix indicates you have an aromatic ring. It explains why this is. If you look at the Nix, overall, this molecule on the left has a more negative Nix. So overall, it's more aromatic, and the tautomer is less aromatic. When you photoexcite it, then your A form now becomes very anti-aromatic because 6 pi electrons in the excited state is anti-aromatic. Now, proton transfer to the other side will give you a tautomer where it's still more or less aromatic. And so in this way, in the ground state, the aromatic form dominates, but in the excited state, proton transfer happens and the quinoid form dominates, because proton transfer is an example of excited state anti-aromaticity relief. Now, for a lot of people, the other interest in this type of molecule is to control the emission spectra. So remember the Weller experiment of salicylic acid, where he sees the salicylic acid, after shining a light, he sees a double emission because of the formation of the tautomer. Now, the formation of the tautomer can have different emission depending on, in this case, depending on if you fuse a benzene ring here or if you fuse a benzene ring here. So here's an example. You fuse the benzene ring here and you have a shorter wavelength emission. You fuse the benzene ring here and you have a longer emission wavelength. And we show that this also this also can be explained by differences in excited state anti-aromaticity. So now I highlight the features here. You see on the left side, in this structure, when you fuse a benzene ring here, what happens is that you can draw a resonance form so that you can have two Clar sextets, one over here, a Clar ring, so 6 pi electrons in a ring. So this means that in the excited state, this is very anti-aromatic. You have two especially anti-aromatic rings, but it also means that as soon as it emits it relaxes to the ground state, you have two very aromatic rings. And so you have a more anti-aromatic S1 state, and you have a more aromatic S0 state. And so you have a larger energy gap, which gives you a shorter wavelength emission. On the other side, if you use the benzene ring to this position, then the only way to draw a resonance form is like how I've drawn it here. So you have only one Clar sextet ring. And that means you have only one especially anti-aromatic ring in the excited state and one especially aromatic ring in the S0 state. And so this energy difference is much smaller, and so the emission is a longer wavelength. So in this way, a change in ground and excited state aromaticity and anti-aromaticity also can be used to explain and fine-tune this emission spectra of these molecules. Okay, now we're going to expand the scope of the story a little bit farther. So when you have an aromatic molecule and a light strikes on this molecule, it becomes excited state anti-aromatic. And a proton is going to transfer to try to relieve this anti-aromaticity. It doesn't have to transfer within the molecule. It can transfer to a nearby molecule. So an intermolecular proton transfer reaction can happen. Here's an example. This is a solvent catalyzed phototautomerization. Think about this molecule, 2-aminopyridine. So 2-aminopyridine, if you dissolve it in acetic acid, this is going to be the major form that you will get. Now, if you photoexcite it, then the tautomeric form will become the dominant form. Now this, so you have this in the ground state, you have this in the excited state. Now this by itself is somewhat puzzling because we learn in organic chemistry that if you have a polar solvent, and acetic acid is a polar solvent, if you have a polar solvent, then the tautomer that dominates should be the more polar tautomer. But if you look at these are the computed dipole moments. If you look at the dipole moment, it is actually completely opposite to what we expect. So in the ground state, this Q form has a larger dipole moment. So this is the more polar molecule in the ground state. But in the ground state, the A form dominates. Now in the excited state, the A form is the more polar tautomer, but actually the Q form dominates. So this cannot be explained, this trend cannot be explained by what we usually teach or what we usually learn in organic chemistry. Now what we propose that as an explanation is that what is happening is that in the ground state, you have an aromatic molecule that is lower in energy. Now, when you photoexcite it, it becomes excited state anti-aromatic, so it no longer is favorable. And one way to relieve excited state anti-aromaticity is to undergo a double proton transfer. So this time, 2 protons transfer, and they involve a different molecule. Here are some numbers to tell you the same story again, but with some data. So here you have a computed potential energy curve for the double proton transfer of this reaction that I just showed you. Now you see at the ground state, the A form is lower in energy, the Q form is higher in energy, so proton transfer has to go through a barrier. So this doesn't want to happen. You have a dominant A form. Now if you compute the Nix, you see why. The A form is more aromatic, so a more negative Nix value. And if you go to the Q form, you have a less aromatic form. And you also might note that at the transition state, you already start to lose some of the aromatic character as the proton is as one proton is starting to shift away and the other is trying to shift in. Now, if you look at this in the excited state, you see the opposite trend. So here A form is lower in energy, here Q form is lower in energy. Now this time, if you compute the Nix, you see the opposite trend. So now your 4n+2 π-electron ring becomes very anti-aromatic, but the quinoid form is much less anti-aromatic, and so it becomes the dominant form since proton transfer now goes through a near barrierless. If you correct for a ZP correction, this is actually barrierless. It goes through a barrierless process to transfer a proton to the other side to relieve anti-aromaticity. This is just for the computational chemist. If you are wondering, then Cas-BT2 and Cas-SEF Nix results and in the S1 state show the same trend. Okay, so, well, in this example that I showed you, I use acetic acid as the solvent, but you don't have to use acetic acid as the solvent. And you can imagine that if you use an even stronger hydrogen bonding substrate or an even weaker hydrogen bonding substrate, then the effect of anti-aromaticity relief also will change according to that, and that will have an effect on the emission spectra of the tautomer. And so we actually looked at 10 different hydrogen bonding substrates and hydrogen bonded to this 2-aminopyridine. And what you find is actually a very nice correlation between the fluorescence, so the emission spectra, and the emission wavelength, and the change in NICs as the molecule goes from excited state to a relaxed state. Here is another example. So here's another example of proton transfer involving other molecules. But in this case, we look at an example of photoacids. So the effects of excited state anti-aromaticity relief you also see in photoacids. These are some examples of photoacids, 2-naphthol and 2-naphthoammonium. So experimentally, it's known that these are not very strong acids. Even if you just look at the structure, they don't look like very strong acids. The pKa values are 9.5, 4.1. Now, what's interesting is that when you shine a light on these acids, they suddenly become very strong acids. So you see this change in pKa going to 2.8. Over here, it goes to minus 0.8. So there's a sudden increase in acidity when you shine a light on these photoacids. These are the changes in the pKa units. These are very, very dramatic changes. Now, following our current storyline, it's actually quite easy to explain this if you consider what happens in the excited state of a 4n+2 compound. So 4n+2 is ground state aromatic, but excited state anti-aromatic. So if you look at the computed NICs for 2-naphthol in the excited state, you have very large positive NICs showing you that the molecule is highly excited state anti-aromatic. Now, if you lose a proton, then you get to this structure. You can actually draw a resonance form where the negative charge delocalizes into the ring, and now that breaches the cyclic 10 pi-electron delocalization. You see this very large drop in NICs value, going from very anti-aromatic to very weakly anti-aromatic. And so you see the effect of anti-aromaticity relief. On the right side, 2-naphthoammonium, you see the same effect. Very anti-aromatic as soon as you photoexcite this 10 pi-electron system. Transferring a proton relieves the excited state anti-aromaticity. Now, something also very interesting to note is that you see the degree of anti-aromaticity relief. A lot of anti-aromaticity relief corresponding to more change in a higher photoacidity, so more change in pKa value. A smaller pKa, a less change in less anti-aromaticity relief, and corresponding to less change in a weaker photoacidity. Here's an interesting contrast to look at the 2-naphthoic acid. So if you look at the structure of this molecule, it actually looks not so different from these weak acids that I'm showing you. A naphthol framework with a substituent, a naphthol framework with a substituent. Here you have another naphthol framework with a substituent. In the ground state, it is weakly, kind of a weak acid. But interestingly, you photoexcite it and it becomes an even weaker acid. It does not follow its structurally similar photoacids. And if you draw the resonance form, it becomes easy to understand why that is. So here's what happens. When you take away a proton from the functional group, the negative charge does not delocalize into the ring. Oh, I drew this differently, but it should have been a solid line here with a negative charge there, solid line here with a negative charge there. But the point is, the negative charge does not delocalize into the ring, so it does not help relieve excited state anti-aromaticity, and you see that effect here. Ground state aromatic compound irradiated by light becomes very excited state anti-aromatic, but upon losing a proton, it still remains quite anti-aromatic. And so because of this, the 2-naphthoic acid is not a photoacid. It does not have a lower pK when you photo-excite it. And this story was recently published maybe 2 months ago. And again, we have this nice cartoon drawn by Lucas. You see here the first one is the 2-naphthol, and he's saying, oh, any idea how we get rid of this anti-aromaticity? And all the compounds decide to give it a try. Very good for some, good, but not as good for some, and quite bad for others. And so if you're interested in reading more about this story, this is the citation. You can look it up on my website, or you can find it on the internet. Okay, now we're going to expand the scope of our story even more. When you have an aromatic compound and light irradiates it, it becomes excited state anti-aromatic. It can transfer a proton to try to relieve excited state anti-aromaticity, like the examples that I've shown you before. It can transfer internally within the molecule, or it can transfer intermolecularly to another molecule. But what also could happen is that instead of a proton transfer, an electron could transfer. And here I want to discuss some examples of proton-coupled electron transfer. Now let's first think about this example here, the OH bond dissociation of phenol. So here you have phenol. Now if you try to break a OH bond, it's not so easy in the ground state. So unless you have a radical nearby, this process of forming a H dot and a phenoxyl radical does not happen spontaneously, and that's understandable. The OH bond dissociation energy is 85 kilocalories per mole. However, if you photo-excite phenol, this process of bond dissociation happens instantaneously. It just readily happens. Now, if you look at these two structures, you note again that phenol in the ground state is aromatic. In the excited state, so you promote one electron to the pi star, so it becomes anti-aromatic. Now, the traditional view of this process, of this bond dissociation process, is that light shines on phenol, and for some reason that weakens the OH bond, and the OH bond breaks homolytically, and you get H dot, and you can actually measure the accumulation of H dot being produced. And so that's the traditional view of how this happens. We don't think that it happens this way, because if you consider the effects of excited state aromaticity on a molecule, what really should happen is that when light shines on the chromophore of this molecule, which is the pi system becomes very unhappy. It becomes anti-aromatic. And so what really should happen is that an electron should go away from the ring. And so in this case, one of this electron, the photo-excited pi, the electron that is excited to the pi star orbital should go away. It goes to the H, and then the bond breaks heterolytically. The bond breaks heterolytically to give homolytic products. Now this may sound counterintuitive, but it actually makes much more sense, because if you consider the electronegativity of oxygen versus hydrogen, oxygen is 3.5, hydrogen is 2.1. It's much easier to break a OH bond heterolytically than homolytically. The point is that photodissociation happens at the sigma OH bond, but the chromophore actually is the pi ring. And this mechanism is a way, this is showing how a molecule relieves excited state anti-aromaticity. Here are some numbers to show you the same story that I just showed you. So let's look at the structures on the side first. So you have phenol in the ground state. You compute Nix, and it shows you that it is a ground state aromatic compound, large negative Nix. You photo-excite it, and you have a large positive value showing you that it's excited state anti-aromatic. And so what this plot is showing is that as you stretch, so the x-axis is the OH bond distance. So you're gradually stretching the OH bond, and you're seeing what effect that has on the energy in the ground state as well as in the excited state. So let's look at the orange curve first. you have phenol, and you start to stretch the OH bond, and the energy goes up. It takes quite a lot of energy to completely break the OH bond. So remember I said before that the OH bond dissociation energy is roughly 80 kilocalories per mole. That's where it comes from. You stretch it, it takes a lot of energy to do so. Now, if you photoexcite it, and the excitation happens again, the chromophore is the pi ring. So you photoexcite the pi ring, it goes to a pi to pi star state. That's the yellow curve here. Now, but as you stretch the OH bond a little bit, you see that what happens is that the reaction hops to another curve. It hops to the pi to sigma star curve. So that's when the electron leaves from the pi system, goes to the H, and you go to a pi to sigma star state. And from there, it's all downhill. So really, the barrier to this heterolytic dissociation giving homolytic product is only 15 kilocalories per mole. And you see that the product here is modestly aromatic, or you can also call it non-aromatic. But this is another example of anti-aromaticity relief through electron transfer, coupled with a proton also leaving. Okay, another example of this proton-coupled electron transfer that may be more familiar is the photo deactivation of the Watson-Crick base pairs. So here I have a scheme showing, I'm using AT pair, adenine-thymine pair as an example. Am I good on time? Yeah. So here you have adenine and you have thymine. And so the thing is that when you have, when there's UV irradiation on your DNA, what could happen is that you might get a mutation in your DNA, but that doesn't happen every day. And the reason why it doesn't happen every day is that when light shines on your DNA, there is a certain mechanism that gets rid of this energy. And this is the mechanism of how your base pairs gets rid of the energy. So you have a base pair here, the light shines on it and it gets photoexcited. Now, if it stays in this state for too long, something bad could happen because it could undergo all sorts of reactions to give you bad mutations and bad effects. But that does not happen because what instead happens is that a proton-coupled electron transfer reaction will happen. You hop to another surface and you quickly deactivate. So this is kind of a protection mechanism for that is inherent to your base to the DNA base pairs. So here you see the ground state curve. It goes to a locally excited state curve, and as an electron and a proton transfers, you go to a charge transfer state, and from there, if the energy of this brown curve is low enough to cross with the blue curve, then it goes through a conical intersection and it comes back to the ground state. In our latest paper, we are showing that this effect, actually it's published today officially. This whole effect also is governed by the effects of base pairs being aromatic in the ground state, having excited state anti-aromatic character in the excited state, and then transferring an electron and a proton to relieve anti-aromaticity. So in fact, this PCAT process is an example of anti-aromaticity relief. So here are some NIX numbers to show you. In the ground state, adenine, thymine, you'll notice that adenine has large negative NIX values, and it's easy to see why. If you count the electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, you have 10 pi electrons. So that's a typical ground state aromatic compound. Photoexcitation usually happens on the purines, so the structures that have a 5-membered ring and a 6-membered ring. Photoexcitation happens here, and then you see that now you have an overall quite anti-aromatic structure, and it's localized. This anti-aromaticity is mainly on this adenine fragment. So adenine is ground state aromatic, it becomes excited state anti-aromatic. Now what it can do to relieve anti-aromaticity is to quickly transfer an electron to the other side, and that follows a proton transfer so that the overall charge is 0, and then you get to this charge transfer state. Now look at the computed NIX for the charge transfer state. You see that it is modestly aromatic. And so this process, in effect, is another example of anti-aromaticity relief through proton-coupled electron transfer. The resulting charge transfer state is modestly aromatic, and so it brings the energy of this brown curve low enough so that there is a possibility of crossing with the ground state through a conical intersection. And so in this way, the adenine base pair can have a very nice and fast photo deactivation pathway of relieving the extra energy brought by irradiation of light. Guanine cytosine base pair, you see the same effect. Ground state aromatic, mostly the guanine base pair is aromatic. So here you don't really have a completely cyclic delocalization in the purines, but if you count the electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Here you have a little bit of a breach, but you can also consider that the CO bond is polarized more towards the oxygen. So you would probably put a little partial positive charge here. So in effect is still considered a Hucol aromatic compound, and you have a negative Nix. You photoexcited, and again it happens on the purines, and then you see that you have a large positive Nix value. Proton-coupled electron transfer relieves that excited state anti-aromaticity. You get an aromatic structure, and from there you have that lowers the charge transfer state enough that it can cross with the ground state. And so in this way, the guanine cytosine base pair has a fast photo deactivation pathway to relieve this energy brought about by photoirradiation. So another example of anti-aromaticity relief through pKit. Okay, so considering the Watson-Crick base pair, at this point, an interesting question might come up, which is whether or not the Watson-Crick arrangement is special. Certainly, if you have A, G, T, and C, there are various ways of hydrogen bonding. So why AT and GC in the specific arrangement? There's actually been some experiments done in around 2005, where these groups find that only the structures assigned as Watson-Crick have broad UV spectra, which suggests a rapid internal conversion. So this is saying that, interestingly, the Watson-Crick arrangement has a very fast photo deactivation pathway, and other types of pairs don't seem to have this special photo stability. And so here's an example. We looked at some Houstine base pairs of A and T. So again, it's still adenine and it's still thymine, but it's just hydrogen bonded in a different way. In the ground state, you see that adenine is aromatic, thymine is more or less non-aromatic. Photoexcitation happens on adenine and it becomes very anti-aromatic. But now, after proton-coupled electron transfer happens, so one electron transfer, one proton follows, you get to this charge transfer state. You look at the computed Nix and you see that it is still more or less an anti-aromatic structure, which means that it's still pretty high in energy. And so the effect, the net effect is that this brown curve does not come low enough. There is not enough anti-aromaticity relief, or your result is not stabilizing enough, that the two curves do not cross. And so this photo deactivation pathway does not happen. It has to find other ways of deactivating, which maybe takes longer time. You see the same effect here for the GC. Here's a non-Watson-Crick hydrogen bonding mode. Ground state, guanine is aromatic. Excited state, it becomes anti-aromatic. Proton-coupled electron transfer gives you this structure, which is more or less non-aromatic. And so it also does not bring the curve low enough to cross with the blue curve. And so you don't have this nice deactivation pathway, which means that this pair, if photoexcited, must deactivate through some other pathway. So these are just some of the examples that I selected from this work, but what our finding actually means is suggesting is that the Watson-Crick base pairs, they're not just electronically complementary. It's not just that AT and GC work well because of this hydrogen bonding mode, but they also have something special photochemically. The photochemical complementarity of these base pairs are explained by the effects of ground and excited state anti-aromaticity. If you are interested in reading more about this topic, this is another cartoon drawn by Lucas, and this paper was just accepted in Chemical Science and published today. You can find it on my website, and there will soon be a highlight by Chemistry World coming soon. Okay, I'm going to make an abrupt stop to my talk and make some final remarks, and I'm going to quote Kasha. So what he says, this is a quote from his paper in 1986. Proton transfer chemistry is intrinsically the displacement of a simple particle, a bare proton, but what causes this displacement is a massive electronic structural change in the molecular species involved. And what we are finding out in many, many examples is that this massive electronic structural change is the effect of anti-aromaticity relief. And it can happen with a proton transfer, it can happen with the electron transfer. Many types of photo-induced electron and proton transfer reactions involving cyclic molecules may be explained by the effects of molecules getting rid of anti-aromaticity. I have my wonderful group to thank. Most of the work I presented today were done by Lucas and Jahua, my postdoc, and Zili. And also in collaboration mainly on these topics with Henrik Ottosson at Uppsala University. A little bit advertisement time. Please follow us on Twitter. And we also have opening for one PhD student. If you're interested, you're welcome to look at my website to find out more about it. Oh, and I want to show you some pictures of Houston. So here we have a picture showing the city. And this is our student learning center, a student center at University of Houston. So if you're in Houston, 1/3 of the time, it's going to be very, very hot. You probably cannot tell from this picture here, but right now, it's, let's see what it is right now. Oh, right now it's 34 degrees centigrade. So most of the time it's very hot. But if you're on campus, you don't have to worry because we have these little robots that will deliver some food, good Tex-Mex to wherever you are. Thank you for your attention. So that's the end of my talk.
Thank you, Julie. Thanks a lot for the wonderful talk. It's a very inspiring one. So there are some comments in the chat for you. For the audience, you can read later on.
Okay.
So I'd like to know if someone has some questions, please. Some comments, don't be ashamed. Comments?
I guess I'm still sharing screen.
Andrea, please open your microphone and you can.
Okay, good afternoon, everyone. Judy, thanks for this inspiring and wonderful presentation of your work. I'm a colleague of Claudio, but in the inorganic department, organic chemistry department, and I'm very interested in.
How can I see you?
I'm sorry not, but maybe you can see my photo there. I didn't come today, so I don't want to open my.
Okay, that's fine. That's fine. I just couldn't see your name, so I'm not sure which one is you.
Yeah, I'm André Formiga.
Okay, André.
Okay.
I will try to pronounce Andrea.
That's fine. That's wonderful.
Oh, I see you, André. André Luis Barbosa Formiga.
Formiga, that's me.
Yeah, I see you. Your picture.
Okay, Judy. Judy, I'm very interested in proton-coupled electron transfer. I do work with this. Some of the reactions that we study in our lab can be classified like that. I'm interested in artificial photosynthesis. And I must admit that I never thought about anti-aromaticity as a driving force to shift the positions of protons. Okay, so my questions are general and mainly driven by curiosity. Okay? The first thing is that all your pictures, they gave me the impression that you consider all the proton transfer like concerted proton transfer. Okay, I just want to check with you if this is the main mechanism that you are studying. And the second thing is that I always think about the proton transfer, like you do, a way to get rid of energy. But in my point of view, the main thing is that you can decrease charge separation. Okay, so the molecules that I work always do some kind of charge transfer, and the excited states that you study are more localized in the ring. Okay, something like that. But they do cause the same kind of transfer. Okay, so I was wondering if there is how can I say that? If there is a fundamental physics behind both processes, you know, and I was thinking about charge separation. So if you could comment on that, if you ever thought about these ideas, it would be nice to hear you again. Okay, thank you very much, you and Claudio, for this.
I will have to take a look at your website later on to look at what types of molecules you usually work on. But I will try to answer this question in maybe not a very direct way, but my view is that a lot of times when you see this either proton transfer, proton-coupled electron transfer, these chemical phenomena, there are two sets of language that you can use to explain them. So there's the physical terms that you can use, but there's also the organic chemist terms that you can use. So for example, when we were working on this DNA base pair paper, one of the reviewers' comments was that, oh, why do you even mention the effects of aromaticity? Why don't you just say it's a difference in the ionization potential and the electron affinity of the electron giving and the electron accepting base? And that, I think, is a physical term. But I think a lot of times the physical term, it is not wrong, it is there. Like what you mentioned, the charge transfer effect, the charge separation effect is there. But I think when you try to describe it in the organic chemist term, then it makes it easier to relate to a structure when you see it. And so I think I like both terms, but I think they have different, they bring different perspectives to the table.
Thank you, Judy. You do some very nice CAS-SF calculations, so you probably get very reliable.
I don't do them. My students do them.
Yeah, your students, okay. But you may have very reliable dipole moments in your systems, not only for the isolated molecules, but the pairs that you have. Have you ever seen any correlation between this?
Maybe we should take a look at, we didn't think about that, but I think we should take a look closer at the effective charge separation.
Thank you, Judy. Congratulations. I'll follow your work, okay?
Oh, we follow each other's.
Yeah, thank you.
Thank you.
Thanks, Andrea, for these questions. Judy, there are some questions for you in the chat. You can read it. It's
oh, wow. Oh, I see it now.
Yeah. They're asking you about...
Andre's question, Andre already... Oh, there is one question, but I cannot answer. How to choose the wavelength to break a specific bond? That I usually rely on my experimental collaborators to figure it out.
Okay, but there is another one.
We work with a lot of experimentalists because they usually they have the good problems and they also know the answers to questions like this.
Okay, and Murilo has a question for you as well. You can read it?
Murilo,
Before...
okay. if these studies in anti-aromaticity could be applied, for example, in the stabilization of photo-unstable polymers, I think yes. I think the thing is that I feel like for a long time, people put a lot of emphasis on focusing on aromatic molecules. And the main reason is because we can make them and so we can do something to them. But I think in recent years, or let's say the past half a decade, people are paying more attention to the effects of anti-aromaticity because we now realize that we can actually make molecules that have anti-aromatic character and that are persistent enough, they stay around long enough to do something. And so I think there is certainly opportunities here. I have not looked at it into it myself, but I think overall this general area of either ground or excited state anti-aromaticity and the applications of it in different chemical fields is a very good. There's a lot of opportunity there. Thank you, Murillo. Murillo.
Okay, thank you. I have just a comment. I don't know if someone has some questions. You can write in Portuguese, very simple one, and I can try to translate. If someone wants to do some questions in Portuguese, you can try to translate to Judy. But I was curious about the paper in the PNAS. So the National Academy of Science, the American Academy of Science, is very formal, isn't it? Because they ask you to change the title of the paper.
Yes, they did. That we were a little bit sad about that because we thought that our original title was more fun, and also especially I have it here, the cartoon.
Yeah.
We could not publish this, but we published it on the mug, as well as this one.
Yeah. So they are very formal Academy of Science. So. Yeah. And Judy, No, sorry.
Yes?
Please, go ahead. No, please go ahead.
Oh, no, I was just going to say our recent cartoon drawing from Lucas, again, that we submitted to Organic Letters, they also thought it was not formal and serious enough. So right after this talk, I have to try to draw something that is more boring, and hopefully they will like it better.
Yeah. And did you mention about the Watson Crick base? So did you mention about the light? When you shine light on this, you have the process to release the anti-aromaticity and so on to transfer. But if you have a peroxide or this kind of DNA damage, do you have an idea if the process is the same or not?
You mean like if you have a peroxide and you just generate a radical?
Yeah. So
see that's I don't know the answer to that, but we thought about that actually but in a slightly different sense. So after you generate the radical, it will start to pass through the bases. And so we have thought about whether or not how easily it is for the electron to transfer may depend on the base and the aromatic character of the base, but we haven't we thought about it in a playing around way, but we haven't done anything.
Yeah. Chemically is different. The process is different because
the process is different.
Yeah, but I don't know if the kind of repair can follow a similar pathway or something like that.
The process is different, but I think it also could be driven by changes in aromaticity and anti-aromaticity. Because if you think about benzene, you excite an electron from one of the degenerate set of orbitals to the higher lying pi star. That configuration is very similar to just taking benzene and then just adding an electron to the pi star. So the effect may be similar. It may be a little bit less, but it should be. You see what I mean?
Yeah.
Yeah. So I think it may be related.
Yeah. Okay. Yeah. Thank you. And Judy, there are some questions as well here.
Is there a website with these cartoons? Oh, there is. Well, there is not a. We should make one. if Lucas is on YouTube, you should make one. In NICS is an NMR measurement. Oh, okay. The NICS is a computational tool, but you see from the name, nucleus independent chemical shift. So it is actually a computational NMR measuring the chemical shielding, and then we convert it to a shift. But it's nucleus independent, which means you don't need an actual atom to be the probe. But it is a computational method. Let me see if there is a. I think I answered all the questions. Yes.
Yeah.
Oh, I can actually respond too. I did not know. Okay.
More comments, questions, please. No, so if someone has some questions, can send an email to Judy later on. So
yes, if anybody is interested or would like to ask questions, you're all welcome to email me about it.
Yeah, there is a PhD position opened as well. If someone are interested.
Yes, if someone is interested, please apply.
Yeah. So Lucas
Houston
applied.
is very nice. Houston is very nice in the winter time, especially.
Lucas is a Brazilian guy. Lucas started his PhD here at the University of Campinas, and then moved to Houston. Lucas is in your group.
Yes,
this is the
yes.
second year or the third year?
He is starting his 4th year, I think.
2017.
Yeah, he is starting his 4th year.
Yeah.
He is an excellent student.
Yeah.
But if any of you are interested, you can also contact Lucas first to see what it is like working with him.
Okay, Judy, if nobody has more comments.
Okay, thank you very much, Claudio. I enjoyed talking to everybody.
Yeah, so I'd like to thank you again. So it's really nice. Really appreciated your talk, the way that you present. So it's very easy to follow, especially for the background of students are different. So you talk in a very nice way that everyone can follow. So someone commented. Someone commented that you gave a very clear lecture. So thank you. Thanks a lot.
Thank you, Claudio.
I hope to see you soon.
Thank you, everybody, for listening.
Okay.
Yes.
Thanks for everyone. Bye-bye. See ya.
Okay, bye-bye.
I just opened my camera just to say bye-bye. Thank you.